All right, how's everybody doing tonight? Okay. Hopefully you got my email about the lack of communication or slowness of communication and all the above. Had a family member, I think I told you guys last Thursday what was going on. Anyway, he passed since then, so we're doing funeral arrangements back and forth between here and Missouri, so kind of hectic, but anyway, thank you for your patience, appreciate it. Last week, I believe you were supposed to turn in your topic for your research paper. If you've not yet done that, please do so. I will accept it late if you have not done that yet. Tonight, we're going to go over basic networking associations that set up all the rules for everything we do in networking, from NIC cards to wireless, wired, and then we'll end on watching a video called Warriors of the Net that talks about and shows how data travels when you click on a link on a web page, how data travels from that web server to you and all that entails as far as data packets go. So it's a good little video, so hopefully you'll enjoy it. This week in week 3, forgot to tell you, last week we do this each week for our lab. All I need you to submit in each week's lab is your full name. So as soon as you come in every Thursday, you know we're going to be doing the lab, regardless how long it is or how short it is. So go ahead and submit your name in week 3 lab if you have not yet done so. That way I can give you points for being here and doing the lab. Tonight it's actually watching the video. Next week we'll be doing a lab on pinging, and then we also have one on setting up a small LAN, local area network. You'll be doing that one, and the week after is creating Cat5 cables, straight and crossover both. You'll be creating. So you'll get to take those home as well. I know some of you have created cables already, so you'll be my gurus for your area to help out. The deal on that night is when you come to class that night, which is 2 weeks from tonight, I believe, you'll start doing cabling. I'll show you how to do it. I'll demo it real quick. No pressure on that. Let you go and do the deed. And then the only rule I have is if you need to take a break, you can just take a break. But each section of the room that you're sitting at, everybody has to complete at least a straight or at least a crossover cable. You can, if you complete the crossover cable, make a straight cable. You're not required to, but a lot of students do because they have time. But everybody at your table has to create the crossover cable. And so you can be there as a mentor and as a helper when you create your crossover to help your neighbor. The main thing with cabling is patience with yourself, okay? Take time, get a good night's sleep the night before if you can, if that's possible. Try to have the best attitude as you can. Don't drink 10 cups of coffee before you come. Well, for some of you it might work. And again, just have a good mindset that you're going to complete it. And so I will tell you, this is now my 40th time teaching this class, 100% of the students have completed this lab from all age ranges and backgrounds, from 18 years old. I think the oldest student I had in here was 89 years old, took this class, my second year teaching it, and completed it with flying colors. So, it doesn't take, some students believe it takes, really strong hands to do it. It doesn't take really strong hands. Again, a lot of it is just patient and a mental state. All right, and we'll talk more about that next week, kind of get you prepped for it, but don't freak out about it. You'll do great. You're going to be creating, in fact, if you look at the back of the room, the red cables, generally crossover cables are red in nature, or they have some type of red tip on the end of it to denote crossover, meaning you can connect it between 2 computers to communicate without a switch or a hub. Straight cable is like you have on your computers, connecting from your computer to the switches on your table. And that switch does what's called a crossover within the switch itself that crosses the cable for communication. And the crossover cable, the wires there's 2 wires different on both ends, and that's what causes a crossover connection. On a straight cable, the wires are the same on both ends as far as the connection wires. And so we'll do what's called A and B wire schism is what it's called. And so 802.11a and 802.11b is what we'll do. And Cat5 cable and Cat5e, Cat6 cable. And I will pick the one I like to use. Some of them up there, they're at the top there, I don't like so much, so I'll pick the best one that I think is best for us to use and the easiest for you to use. Okay? All right. So this is week 3, chapter 2 review questions are due, chapter 3 quiz. Let's get started on the discussion. So standards. Oh, everything that you do in life has standards, right? As boring standards, they are boring. I'm not going to say they aren't. All of these standards we're going to talk about tonight are hard. You can download them hard copy. You can view them via PDF. They're called white papers, and literally volumes and volumes and volumes of standards have been written for everything in networking, from the Ethernet that you're on right now to wireless to everything in between. So a standard basically is just an agreement that's a documented agreement that gives specifications and stipulates a minimal standard for that whatever it is. Okay? In this case, a minimal standard for a NIC card, a minimal standard for wire, whether it be wired or wireless. So documentation for networking standards are the minimal requirement needed for manufacturers to create whatever it is that they're creating for a network, whether it be a NIC card, a Wi-Fi access point. Standards important in the networking world is, as you can imagine, there's tons of different hardwares out there, right? Hardware providers, from 3Com to Intel to a whole slew of other ones that create network appliances. Cisco, you've heard of them. And so, you know, tons of other ones. I won't mention all of them, but, you know, list is pretty long. All of the folks that create network hardware and software both have to abide by some standards so things can talk correctly on a network. If they don't abide by those standards, a lot of them are, some of them we'll find out tonight are like voluntarily standards. Voluntarily, these companies abide by these standards to put the stamp on approval. But for the benefit of the company and sales, it's probably best that they fit within standards that have been laid out. So again, last bullet point, it's a minimum standard. An example, if you installed Windows 10 recently, or Windows, we'll say Windows 10, it's the most recent probably for most of you. It had on the software, here's the minimal requirements for your computer to install this software. We'll just say, for argument's sake, it was 12 gigs of RAM and a quad-core processor and 60 gigs of hard drive space, whatever. That's a minimal standard, right? Now, that's not optimal standards, that's just minimal standards, meaning to install it and run, that's what it needs. There's minimal standards for network operating systems, there's minimal standards for setting up a LAN, a local area network, minimal standards for Wi-Fi. All the things we do in networking, there's all minimal standards out there, and it's all documented in literally thousands of pages of standards that people write. And so if you are a writer or you like to meet, which I don't like meetings a lot, but if you like meetings that are productive, I don't mind those, but if you like long meetings to where you're documenting and creating criteria for something, whatever it might be, or some of you might like that, because some people, thank God, do like that. Otherwise, we wouldn't have standards. You might want to think about joining some of these standards groups as time goes on. And there's a lot of different organizations. The first is that oversees computer standards. Examples, ANSI and IEEE. Talked about IEEE already in here, I believe, in week 1 or 2 on the student chapter of IEEE. I encourage you to kind of go on the website, see about it, and see what's available. A lot of cool stuff. There's a nominal fee, but it's definitely worth it. It's not as expensive as a normal member, a non-student member, but it's a really good one. These guys set wireless standards, ANSI and IEEE. And ANSI sets particularly to the type of NIC standards, right? So 3 Common Intel are the top 2 NIC creators. Network professional responsibility is to be familiar with these standards and understand how critical it is to buy hardware and software that has a stamp of approval of these standards, specifically in this case, IEEE and ANSI. And you can literally see on these hardware devices the stamp of ANSI and the stamp of IEEE standards on these hardware devices. So ANSI's been around for a while. It's the American National Standards Institution. It's 1,000+ representatives, quasi between industry and government. And so kind of a good mix of governmental and people are actually boots on the ground workers that do the work in factories and create this stuff and are inventors of this stuff. They determine standards for the electronics industry and other fields. And so there's constantly, as you can imagine, people inventing things on a daily basis, hundreds and hundreds of patents, if not thousands, on a daily basis created for networking, whether it be in home or whether it be in business. And so folks, a part of these, it's checks and balances basically. Government, you need that to pass laws. You need those guys and gals. Industry, they have the understanding of what's needing to be passed. And that takes time, by the way. A lot of red tape there, a lot of red tape. And it's not everybody can fit in that group, right? Myself, probably not so much because I'm too vocal, probably is a good term for it. And sometimes I'm not real politically correct, maybe, might be a better term for it. And so, but I do know students that have went to Rock Valley that have wanted to be a part working in lobbying for standards over the years that did a great job and has done a great job. So it's, again, you might be that as well. Again, you have to have a technical mind, work in the field, but as well as understand some government and are interested in government, interested in law. And it's a critical part because we have to have people be a part of these standards groups. Request voluntary compliance with standards on ANSI, meaning, again, this is not a you must do this, it's a voluntary thing. And so if you buy any say Wi-Fi device tonight, you go to Best Buy or you go to newaid.com and look at any Wi-Fi device, doesn't really matter. You will notice somewhere in the documentation for that Wi-Fi device, that access point, the router, whatever, the ANSI stamp of approval on that device, more than likely. If they're selling and they're popular, they're definitely going to have it, and they want to be popular. Obtaining ANSI approval is rigorous testing because the law folks and government aren't testing it, but the folks in the workforce are testing these devices on a continual basis. So if there's a new patent out, a prototype's created, there are entities that actually can test these devices and say, yes, we put this ANSI stamp of approval on this device, okay? And it's not just a device, you're talking about hardware for the device, right? Software that runs the device, functionality of the device over Wi-Fi, so they test all of that. ANSI standards are available online, and they are called white papers that, again, multiple thousands of pages of documentation. EIA and TIA. EIA is basically Electronic Industry Alliance. They're a trade organization represented from the U.S. manufacturing firms. So a big Midwest stamp here, as you can imagine, being the hub for manufacturing here in Rockford and Indiana, Missouri, Wisconsin. They set standards for its members, help write ANSI standards. They lobby for favorable computer electronics industry legislation for new products coming out. Okay, an example: if Cisco is creating a new Wi-Fi access point with the newest and greatest pushing the envelope technology, it might take them 3 to 4 to 5 years to get that technology pushed through legislation to be a standard for everybody to use now across the board, not just Cisco, but maybe everybody can use it. And that's a great thing too about these standards organizations. Once a standard's been approved, then other companies or other inventors can then use that standard to help capitalism and help build economy and create jobs and stuff like that. So it's really a good thing. TIA, Telecommunications Industry Association, is a subgroup of EIA, and they are former United States Telecommunications Supplier Association, USTSA. The focus of this group is to make standards for information technology, wireless, satellite, fiber, telephone, and fiber optics, telephone equipment and fiber optics. The TIA EIA 568B series, that is a series that you'll see on the cabling when we do the lab here in a few weeks. You'll actually see a 568B on the cable sheath itself, saying it's a stamp of approval with this 568B series TIA EIA guidelines for networks cabling, both commercially, mainly commercially, not for residential, but commercial, even though it's installed in residential. So you'll actually see that lettering when we do that cabling, and I'll make sure and have you view the cable and see the little writing on there in black that'll say this TIA EIA 568B approval. It means approved by that standard. IEEE, Institute of Electrical and Electronics Engineers. It's a international engineering professional society. They do meet here monthly, by the way, and then they have regional sections as well for student groups, and Chicago and Schaumburg area as well meet. The goal of this group is to promote development and education in the electrical engineering and computer science field. So if you want to go into networking, programming, electronic engineering, IEEE has all of those. They host symposiums, conferences, chapter meetings, student chapter meetings. They maintain a standards board, and they have a lot of technical papers as well, and very, very, very highly respected group. And then again, IEEE is something that I do recommend to students, at least trying it out, going on their website and seeing what they have to offer, and at least subscribing to that, whatever you can while you're here on campus, and getting the discount of being a student. ISO, International Organization for Standardization. I've always wanted to go. Their headquarters in Geneva, Switzerland. It'd be kind of cool to go there. Collection of standards. They represent 162 countries. The goal of ISO is basically to establish international standards for barrier-free trade and widespread authority throughout all of these countries. ITU, International Telecommunication. They started in United Nations, which started in '48, I believe, and regulates international telecommunications, provides developing countries with technical expertise and equipment. Founded in '65 and then 47, not 48, joined United Nations in '47, and members from 193 countries. Focus, global telecommunications. So basically, like my cousin was in the Army, and he worked with this group, ITU, part of the Army. They provided hardware, they provided satellite, they provided makeshift tents and buildings for school children and communities to have free Wi-Fi and computers and a whole bunch of cool stuff. And he went back the last 2 tours just to do that for elementary kids. And he spent 2 summers doing it and loved it, and knew nothing about technology before he joined it, and then learned everything during that 2-year period of how to go in and set up from scratch a Wi-Fi, basically cafe for a community, which is pretty cool, pretty rewarding. ISOC is another, founded in '92. It's the Internet Society, professional membership, technical standards for internet. The goal for these guys is internet growth, okay? IP version 6, which we currently have as the latest standard, is stemmed from this group. They saw about 5 years ago, 8 years ago, the fact that at one point, I think they predicted 2030 or something like that, we would run out of IP addresses or come close to it. When they mean run out, maybe still have 5 or 6 million left, but still, that's pretty close. So IP version 6 came out, which basically gives a longer range of IP addresses, a wider range of not just IP numbers, which IP addresses are made currently now in version 4 of just numbers, to letters and numbers both, and special characters in IP version 6. And so keeping internet accessible, information security, stable internet addressing services, and open standards. And IP version 6 currently, if it's new hardware anyway that's being built, has in it both version 4 and version 6. If you buy a new laptop, desktop, regardless what the platform, and even your phones, a lot will have both version 4 and version 6 alike. ISOC continued. It oversees with a specific mission board. The first is IAB, the Internet Architecture Board. It's a technical advisory group that oversees the design and management of the internet. IETF, Internet or Engineering Task Force, sets internet system communication standards, particularly protocols for operation interaction, and anyone can submit a proposal. Very elaborate review, testing, and approval process. This ISOC group, going back to my cousin, they had to create new standards because they were going in regions and having to do things they hadn't not been able to do, had just not done before. And one of them was using satellite satellites plural, for widespread internet coverage to, like, say, a region of a country. It was possible before. There was just limited hardware that was cheap enough to do something with. So they created new standards to create hardware that was literally $35 to $50 a piece to give a community access to the internet, which was unheard of at that time. And so this group helped build, during the testing review standard, build a system in order to communicate with satellite. IP address, Internet Protocol, addresses identifying computers, like in your computer in front of you, your phones, your laptops, desktops at home, all have unique IP addresses. This group basically is for global IP addresses, meaning websites, domains like GoDaddy is a part of this that helps this management system. Domain registrars, that when you have a company here in town and you want to host your own web server, like here at Rock Valley, we host our own web server, and we're through Illinois Century Network is the ISP, and I think we've got 3 external IP addresses exclusively for Rock Valley. I mean, nobody else in the world has those IP addresses, and every business in the world that has a website has a unique IP address dedicated for that website. And so, as you can imagine, somebody's got to manage that list, right? That can be quite daunting to do. And so that leads to the IP address management history. It first started out initially with IANA, the Internet Assigned Numbers Authority. And generally when you have technicians, or we'll just say technicians to be general. When you want to create a name, that's what you get. There's not much creativity. So Internet Assigned Numbers Authority, sounds great. So that was the name. Made sense, you know, just by reading it, what it kind of did, right? Wasn't gray at all. 97 then sprouted what's called 3 registrars. One was ARIN, American Registry for Internet Numbers, APNIC, Asia Pacific Network Information Center, and then RIPE, Réseau IP Europeans. So 3 entities in 97. 90s came in the ICANN for what's called the Internet Corporation, late 90s, for assigned names and numbers. Basically, it's a nonprofit 501c3 organization that's responsible for IP addressing and domain management. And the IANA performs the system administration part of it. Users and businesses both alike obtain IP addresses from ISPs, like for instance Xfinity. If you have a business class Xfinity, they will give you 2 or 3 external IP addresses, and then you pay so much for those IP addresses. And then this group, ICANN, keeps track of all of those numbers. In fact, it's called, and technically the technical word for it is called the WHOIS database. If you just Google the word WHOIS, all one word, you'll see a whole bunch of links to where you can look up any domain. It'll give you the WHOIS information about who this company is, who registered it, what's their email address, what's their contact information, what's their fax number, or if they use fax anymore, what's their email, phone number, all that good stuff. OSI model, switching now from standards to process, okay? In IT, I would probably venture to say pretty strongly that a lot of issues in networking or anything in IT in general have to do with people not following process. Now, my wife used to work for a cardiologist for years, and one of his big pet peeves, I always heard him say, picking her up from work and hanging out with him. His name was Dr. Harner, by the way. He's a cardiologist. He's retired now, but he was really funny. He's a Swedish guy. And he would say, this building needs a system and needs a process. Without a process, things don't work. And I'd go a step further. You can have a process, but if people don't follow a process, then it definitely doesn't work, right? And we could probably use that in every single type of business or whatever. So with this group, basically, the OSI model it's not really a group, it's a model for networking folks to put in a model here where things go, where communication goes on a network. It was developed by ISO in the 80s. It's divided into 7 different layers. And again, it's a model. There's not hardware, software involved, or any company. It's just a model, you'll see. So 7 layers. You have physical layer, data link, transport, or network transport, session, presentation, and application. Protocol interaction, meaning it usually interacts with a model above and below it. It does interact with software, but it's not software. The physical layer does act on the cables and your NIC card and connectors to switches and hubs and routers and such. It's theoretical, it's not perfect, it's just a model, okay? It's hardware and software independent. Every network communication process is represented. And they have what's called PDUs, which is protocol data units. It's basically just its way of determining the flow of data on a network. And it flows through layers 6 through 1, you'll see in a second. And it's a generalized model, but imperfect. So here's what it looks like. So 2 computers, left and right? We'll start with the left one. Physical path, NIC card, okay? Going down in the application. Application we'll say is Chrome, and you're running Eagle, and you're viewing the slideshow, and you're viewing a presentation or whatever. Takes it to the next level, presentation. Okay, takes that Eagle, say you're sending an email, you're putting your name in that submission box tonight for the lab. It packages that name in the application, which we'll say is Chrome or something, for most of you use Chrome tonight. But could be Firefox, could be IE, but you get my point. Then it takes from the application to presentation layer, meaning it's taking the data you just clicked submit to, which in this case is just text data, right? Just text data. And getting ready to present it to be going to the network. Then session layer is how long it lives. Session determines authentication. So when you log into Eagle, let's say you have a 10-minute timeout and you don't do anything for 10 minutes, it times out, you're logged out. Session layer determines basically that authentication piece. They call it handshaking of the data, the passing of the data. Then the transport layer and network layer of the OSI are getting ready to convert this data now into digital in just a second. So it's going to go from, say, binary here, which is just text, or not binary, but text version, to digital, which is binary. And so The data link layer and the physical layer is your actual NIC card and the wires on your NIC card. It goes through the network at the bottom there, comes back up through the top on the right side, does the reverse logic, hits the physical layer, which is your NIC card, data link layer, network layer, transport layer, session layer, confirming that it's still authenticated, presentation layer, and then finally pushes it to the Eagle server and saves your name in the Eagle server wherever it's located at. And it just continually goes on and on and on. And so again, application, presentation, session, transport, network, data link, and physical. So the top layer, the application layer, is not actual software, but it works with software. That's why it's called the application layer. Protocols are basically to facilitate communication, intercepts the network request, whatever it might be, and interprets that package. In this case, it's text message, and interprets that data to send it to the network. It negotiates with that application layer protocol, meaning it does formatting of that data, wraps security around that data, and other requirements. Example is the HTTP protocol. Okay, like tonight when you went to Eagle, if you looked at the top of your web browser, you would have seen HTTP. That's the protocol it's referring to, and it falls on the application layer because it's working with an application. In this case, would be your web browser. So we have an example here of a web browser browsing the web, collecting data, requesting data, returning information, all falling upon the application layer while somebody's viewing, like you've been doing tonight when you log into Eagle, a web page. Then it goes to the presentation layer. This accepts the application layer data, formats it. Okay, an example of formatting would be if it's like this one's text, that's a no-brainer, it's just text-to-text format. But might be an image, right? Might be a GIF, a JPEG, a MPEG, a QuickTime movie. It takes it now, presents that layer, and wraps that data type with an encapsulated wrapper. Like an example, text has a certain wrapper, right? Videos have a certain wrapper. MP3s have a certain wrapper. And then in technical terms, it's called encoding. It just encodes it with a certain wrapper, is all you need to know. Another example of a protocol that it might wrap, and it definitely does this in Eagle, is security. There's SSL, because when you log into Eagle, you'll see HTTPS, right? Meaning it's a secure socket layer, and that's also wrapping your communication. Here is what it looks like on the presentation layer. You'll notice the bottom part there, okay, how it's circling that bottom part here. This is where technically the presentation layer occurs, but you'll notice it includes part of the HTTP, and all it's doing here is doing the encapsulation, or which is another word for is presentation. Technical words, encapsulating it, circling it around with something to package it. Then we got the protocol functions in the session layer. The session layer coordinates and maintains communication between the two nodes. It's for ongoing communication when you're logged into Eagle, okay? And we're just using that as an example. But while you're logged into Eagle, it's constantly saying, are you there? Are you there? Are you there? Yes, you are. Are you there? Yes, I am. Yes, I am. Are you there? Constantly doing that all the time. And yes, you will see that type of thing in the video tonight. You'll see a router talking, right? Which you've never seen before. But just to visually help you, it'll help you out. So it's for ongoing communication, and in technical terms, or layman's terms, better yet, it's called handshaking. So while that handshaking is occurring, and it stays static, that handshake and connected, the data can go to the next level. So from session layer and session layer, it keeps that connection alive continually, synchronization continually, because packets can drop. You'll see in the video in a second. Packets can drop, and they'll need to be resent. An example I give students at this point is if you ever downloaded a file, right, or started downloading a file, and it just stopped, dead stop, wouldn't download anymore. Or maybe say you couldn't download it because you didn't have time, and you paused it, right? And then you went back the next day and was able to resume it, right? Just fine, and it completed downloading it. Well, in this session layer, that's where this occurs. So when you're downloading anything from any source, from a network, from a web browser, it's in the session layer protocol where this is occurring. It also, as you notice, can restart your transmission. So if a download halts for a second and stops, you maybe see it restart in a moment after the network is not congested as much, or the internet speeds at your home get better, or people other people try to stop downloading, or do stop trying to download it, and you're able to download yours. It also terminates communications. So when you log off of Eagle tonight, it's in the session layer. Sets terms of communications, meaning an example for Eagle would be username and password authentication. And then identifies every participant in that session. So an example here is a session layer between Internet A phone and Internet B phone. And in between those two are two servers, server A and server B, and then the internet. And you'll notice, starting at the top, you've got a request call from A to B. Okay, go ahead. Still there? Yes. And notice it's both ways. Still there, still there, still there, back and forth. Next, still there, back and forth. Then finally, end the call. Okay. Okay. And that's going on all the time. So basically, like tonight, if you're logged into Eagle, you are at the still there section and still here section of this protocol, right? It's constantly asking, are you connected? Are you connected? Yes, I am. You're saying, yes, I am connected. Are you connected? Are you connected? All the time. Transport layer. This one is basically accepts the session layer, manages end-to-end data delivery. Also, flow control, meaning that handshake I talked about earlier. This is where you get the synchronization of acknowledging that the session layer indeed is successful, and now the handshaking part is back in the old dial-up modem days. You'd actually hear the shriek sound of a dial-up modem. Anybody remember dial-up or see videos of dial-up modems on old movies? When you go, yeah. What was it doing at that? Yeah, it's doing this handshaking part is what it was actually doing during that noise sound. So during that squeaky time of connection, it was synchronizing, not only authenticating your username and password right, but it was acknowledging that, yes, your username and password is correct, the connection's good, and then the noise would stop. Yes?
So what is the noise?
What is the noise? It's actually built in the modem. It was actually a noise maker, basically, that made that noise to let the user know something's happening. Also, though, on the modem itself was lights as well. You had like red light, yellow light, green light. And when it got to the green light, that was the acknowledgement that it was actually connected. Now, if you look at your NIC cards tonight or when you get home, you look at a NIC card on a desktop or something, you'll see those lights as well. A green light blinking. If it's yellow, it's congestion. We might see red, meaning it's not working at all, something's wrong with the connection. So that's your handshake. Next in the transport is what's called a checksum. And all this is doing is determining if the data that was sent, in this case your text of your name, was indeed sent successfully to the Eagle server. And it matches some things. One is it matches what's called a checksum. A checksum is a combination of file size and a unique code combined. And that checksum that was sent with that file, that text name that you sent over, has to match over here on the server. If it doesn't match, it has to be sent again, all right? Because what could happen in between is that data could be compromised, it could be dropped, one or the other could happen. And so when hackers basically do a man-in-the-middle attack on a data packet, it messes with that checksum. And when that checksum doesn't match, the server will know, the router actually will know it needs to resend that data again. Next, you have what's called in the transport layer just connectionless protocols. It doesn't establish connection with another node before checking it. It does not check data for integrity. It's basically used, it's the IP portion of the TCP/IP. It's the just kind of wild, wild west. It's just fast. Speed is what it's all caring about on that one, on connectionless orientation. Segmentation in the transport layer, I like to refer to as, I'll do my nice drawing here, of cabooses on a train, okay? That we'll pretend that this is your text, your name brought across from your computer to the Eagle server, and we'll just use Nick as an example, okay? And every letter is now part of that data segmentation, broken apart in the caboose, sent across the network. On the other end, in Eagle, it puts all of those together to make just your data packet complete. And this data packet can be segmented into millions and millions of different data units, okay? And the reason it does that is a couple reasons. One is, when you split something up into millions of pieces, it's a lot easier to transport it because it's not as heavy on the network. Also, if, let's say, for instance, this packet or this segmentation, this data unit doesn't make it, they don't have to go after the NI and K packet, just the C packet has to be resent again. And the network's smart enough to know that the C packet wasn't sent. The C segmentation was not sent, it needs to be resent again. So you have to resend the whole packet, the whole train, the whole caboose and everything, and all the cabooses, just that one or two, whatever might be dropped. It increases data transmission efficiency on every network type. It says in the book certain, but it's on every network type. Segmentation, I believe, increases data efficiency and transmission efficiency. MTU is a maximum transmitter unit. Basically what that is, it's referring to the size of each caboose. It can be up to 1,500 bytes max. But it doesn't mean it's going to use that. That just means that's the max it can use. And the network decides what that size is going to be. And the router decides that, and then separates it and sends it out. The discovery routine is also determined, used to determine the MTU. Then it reassembles it, like I said earlier. So all of those cabooses that are being sent across, the NICK, are then reassembled together and recombined and sequenced together to be put in one nice file. Okay, so it could be, again, a file you upload in Eagle, a text you send, whatever it might be, a movie. It's all of it are done the same way, segmented, reassembled, and the checksum is checked to make sure it's valid. So here's a good example of a long message sent across the network, and you'll notice the little cabooses there, the little boxes sent across the transport layer. When it gets to the other side, the recipient, it puts it all together and reassembles it and puts it in the right spot. We'll say a database in this case, that is your name for the Lab 3. Then the network layer is the next protocol. It translates the network layer, translates the NIC card, the network address, into the physical counterpart. Not really NIC card yet. There's a network layer that decides from your network, it gives your device a network ID, is what it's called. And that network ID is addressed to you and you alone in that computer. You also have an IP address. You also have a NIC card that has a MAC address we talked about already. And the addressing is basically a system for assigning unique identifying numbers to network devices. In this case, your NIC card is a network device. Okay, so it's going to have a MAC address, an IP address, and a network ID assigned by the network. And there's types of network devices, would be the network address I talked about already, and the physical address, which would be your MAC address of that NIC card. So an example of a network address might be a 10.34.99.12. The physical address is that number there, that alphanumeric number there. Factors that used to determine this is delivery priority, network congestion, quality of service, and the router basically is the one in this network layer that's smart enough to determine everything. It might not be the fastest route, but it'll be the best route to make sure your data gets there. Yes?
Odd question. I know it's in a different layer, but what's the difference between the physical address and the MAC address?
Yep, that's what we're ready to talk about.
They look kind of similar without.
Yep, this physical address is actually the physical address of the network that's referring to on this slide. So notice you have a network address example and a physical address example. Same deal, just one is called a network address, one's called a physical address. And we'll get ready to talk about MAC address in a second.
Okay.
So two separate things in the same family. So then we've got in the network layer, the IP address, it's called the Internet Protocol. And then fragmentation, which is subdividing that transport cabooses into segments performed by the network layer. And then segmentation is preferred over fragmentation for greater efficiency because it breaks apart the datagram or the data packet into multiple cabooses to send across the network in the network layer. Here's what a network layer screenshot IP packet looks like. You'll notice at the top it has a source IP address and a destination IP address. Okay. It also tells you the version of IP here is version 4. Remember we talked about earlier version 4, version 6. The header length is 20. Going down further, some stuff we talked about. Fragmentation, don't fragment set, more fragment not set. Time to live, we'll do a lab here in a bit on in a few weeks on pinging, and this talks about how long that data can live and hop on the network, basically how many hops that can occur on that network. And a hop is like from your computer to your switch to the routers, and we'll say there might be 30, 40, 50 hops that occur between that. Then you'll notice in this the checksum, and it says correct, meaning the data that was sent with that checksum attached to it is correct checksum on the end result when it's put together. Then the source and destination IP address again are noted at the bottom of that IP packet. So data link layer. This functions of this protocol, function of the protocol is basically to divide the data received in the different frames and the transmission of the physical layer. And its whole reasoning for existing is basically to get the data or the payload from point A to point B. So what we've been using tonight as an example is your name going from your computer in Eagle to the web server wherever it's located. We'll say it's located in San Francisco. All right, we'll just say that. And making sure it gets there. And the sender's and receiver network address, error checking, control information, all part of that. Now, there can be mishaps. And you'll see that in the video in a second. Not all information can be received sometimes. Data gets dropped. It's not always hackers that do it. It could just, data congestion happens and data drops. Corrected by error checking. And there's error checking inside of this data link layer, which is all done basically within the network and the network devices, which would be the switches mainly, and the routers on your network. And basically what could cause it is a glutton of information, just tons of information being pushed through a pipe. It's kind of like if we tried to push millions of gallons of water through a straw or something. It'd explode the straw, it'd just be gone. Right? And so same thing with data. Sometimes we're trying to, like for instance, if you're home tonight right now and you were to go online to download something, it might be kind of slow, possibly, 8:30 at night. But say you try to download the same file at 3 in the morning. Is it going to be faster, you think? Why is that, you think?
Less traffic.
Yeah, less traffic. Less traffic in your area, and so it's going to hopefully go faster. That's why a lot of times you'll see like Windows by default do updates at 2 or 3 in the morning. Before you don't have to change anything, it's going to update at 2 or 3 in the morning. That's why it does it. And so hopefully you're not up at 2 and 3 in the morning. Sometimes you are, but it's not normal. Normal time for folks to be up, but normally that's when the drops occur if you have congestion, here called possible glut communication request. Next to the data link layer, there's 2 sub-layers of the data link, the LLC and the MAC. The LLC is a logical link layer, and then the MAC is a media access control sublayer. It basically is the physical medium, appends a physical address of the destination computer onto a data frame, okay? And this is referring to the fixed number associated with that MAC address on that NIC card, which we've looked at some pictures of that already. And you'll be doing a lab basically where you'll be installing a NIC card. You'll physically get to see it if you've never seen one. Picked it up and held it and seen a MAC address. And again, that is unique again to your network. Now, can you do what's called, and we'll talk about this semester, MAC spoofing, where you can spoof a MAC address? You can definitely do that. Spoof an IP address? Yes, you can. But when everything's working great and that's not occurring on your network, things run smoothly. But even when things are running smoothly, congestion can occur, and that's why the importance of addressing is so important. It's not enough just to have an IP address different, you also have a MAC address different, a network ID address different. So you kind of have, the more rules you have for that connection that's different on all devices or all nodes, the more likely that data will get there eventually, okay? Now in today's world, it's a little faster than what it used to be, but still people complain, right? It's human nature. If you're getting downloads of 1 terabyte a second today, and tomorrow it goes down to half a terabyte, you're like, this is dirt slow, right? So, you know, it's just human nature. And so, and you'll see in the video how it talks about the fact that whenever data is resent or packets are asked to be resent, it's in a drop of a hat. It happens very quickly. You don't even notice it. Now, this is basically just a subdivision of network layer and physical layer. The physical layer, as we've talked about already, is your NIC and the wires, right, connected to the NIC. In this case, in this room, would be your Cat5 wire. But it could be fiber, it could be wireless, it could be cell phone. That's all on this media access, this MAC address area. And basically, the data link layer is a combination of the NIC or the network layer, which is the network ID, okay, your IP address, and also the MAC address, which is a physical part of the NIC card, physical number, alphanumeric number, and it also, the NIC card also has, for that MAC address, the manufacturer also has a unique code in there as well. So this is an example here of this is a wireless NIC, by the way, and you'll see it circled there, the MAC address hard-coded on that. And so at manufacturing for this D-Link wireless, which is a real popular way to connect computers wirelessly that you don't want to wire them in your house maybe, you can use these type of NIC cards to wirelessly connect without having to run wires, which is nice. I've used them before. They work really well. The physical layer down to the bottom now. Protocols here, accepts data from the data link layer, accepts frames, generates signals. Those signals, by the way, has a little bit of voltage in it. Not enough to knock you down, but it does have some voltage in the actual Ethernet frame. In fact, you can buy devices, even today, and most students aren't aware of this, but you can go on Newegg and buy them, or wherever. Newegg would be a good place to go, and buy what's called Ethernet over power. And what they are is they're 2 boxes you buy, right? And you plug one near your router, your Wi-Fi router, and say you plug one upstairs or down in the basement, and you literally plug in an Ethernet cord into the device and into your router, one of your ports on your router. Then downstairs, you plug that device in a wall socket as well, plug in an Ethernet, plug it in your computer, and guess what? You have Ethernet over electrical wires in your house. Works great, works like wonders. About 65 bucks, you can buy a pair of them, and you don't have to run Cat5 cable. And it does work quite well. And many people aren't aware of it, and I've used it a lot in installations to where time was at the essence and they needed connectivity, and it works. It's not much more expensive than creating a Cat5 cable and the labor of doing that and the time of doing that. And so if you ever are at a spot where you need to create a network connection between multi-level, multi-layer, multi-floor installations, it will work. It does work really well. I've even used it to connect switch to switch and room to room with power over Ethernet over power lines in your house. So it works really well. Now, the copper within the cabling does have some voltage, like I said, but again, it's not going to knock you down, but there is voltage that sends the signals, uses to send the signal across. Fiber is light pulses. Somebody have a comment? Do what? Very low voltage, yeah. You can hold it with your hand, it's not going to do anything. Fiber, it sends its data via light, and it's either through glass or plastic in the medium. And the wireless, you're all familiar with that, electromagnetic waves, meaning it can be congested by, like, say, microwave. It can be congested by your garage door opener. It can be congested by Wi-Fi, or not Wi-Fi, speakers, wireless speakers, which a lot of TVs have, or a lot of room. Well, you might have a wireless surround sound, right? That can cause transmission flaws. Cell phones, transmission flaws. So a whole bunch of stuff can cause transmission flaws because, again, electromagnetic waves you don't see them, but it can be conflicting with regards to what the megahertz it's running upon. An example would be if you have a wireless surround sound that's on, like, say, a 5 megahertz channel, that the electromagnetic waves will actually go at a certain level in your room, in your house, for that 5 megahertz. We'll say you have a Wi-Fi access point that also functions at 5 megahertz. Same channel. They also deal with different channels, like 1 through 11. Say they're both on the same channel. So a lot of times I've seen wireless surround sounds are usually on channel 6. And so it's simple fix for that is just to change your channel on your Wi-Fi access point to something but 6. So maybe like a 2 or a 3 or an 11 or something like that. And then and when we do the Wi-Fi access point lab, you'll see how to do that. If you don't already know how to do that on your router, I show you how to do it on a Linksys router, which probably most of you have those, or a 3-com router. You might have that as well. Okay, so physical, continuing on, it detects responsibility on this protocol. And again, remember, this is just a model here we're looking at. In fact, I'll stop for a second and talk about the fact that companies will say we are a layer 3 company, we are a layer 7 company, meaning they focus on the certain layers of protocols within those regions, like Cisco. What layer do you think they might specialize in? Let me go back and give you a visual here. We'll go forward, I guess. We'll go to that one right there. We'll go to that visual here of this OSI. So what layer do you think they might? It could be more than one, by the way, too. What do you think? Transport layer. That's the layer 4, ensuring data flow, segmentation, reassembly. What about anybody think layer 3, network layer? Dealing with establishing network connections, translating that network address into physical counterpart. Yeah, probably so, layer 3. Layer 2, packaging. Layer 1, the actual physical part. I would say probably out of all of these, the most strongest one probably would be layer 3, the network layer. I think that's what they specialize in, right? That doesn't mean, though, they don't hit the transport, they don't hit the data link, but because they do, because they overlap. But a lot of companies will say we're certain layer 3, specialize in layer whatever for our company support, right? And some are for support, some are for creation and support, like Cisco. So communication between two systems, we've talked about the OSI. We talked about, first of all, organizations and OSI. Now we're getting into the actual data part of just data, pure data, right? The transformation of a data from your NIC card into what's called the application layer, generating the application layer, is what's called PDUs, which we looked at, which was the data units that's in the cabooses, that's segmented, then resegmented and put back and reassembled on the other end, has a checksum, make sure it's there and valid. If a data packet drops, the router says resend that data packet. And the segment basically is a unit of data that's subdivided in that larger data unit, a PDU. And again, just think of it as cabooses, that's the way I think of it. When I explain to people, it makes more sense to kind of understand it that way, even though there's a lot more technical stuff behind it. Kind of helps you understand a little bit. The packets basically are generated in the network layer, and basically the packets are data with addressing added to the packet. Okay, an example, the text name that you sent across has stamped on that your source IP address on your computer. The destination IP address, which is the Eagle server, okay? Your network ID, your Ethernet, your NIC card ID, sent to that unique server, wherever it might be located. It has a unique IP address, it has a unique NIC card, MAC address, and a network ID as well, all three of those. So it's going to take it and packet that data with that addressing around it, around that packet. So when the network sees it, it doesn't just see your name, it sees, okay, you're coming from this computer, from this MAC address, from this network ID, at this timestamp with this checksum, and this many segmented cabooses. And when it sees it on the server end in San Francisco, we said, it can reassemble those with that checksum and put it all together. Frames has to do with generating the data link layer, which is the several smaller components or fields. And generally a frames, when you remember looking at that IP frame where it had 40 frames, meaning that data was split up into 40 different frames, 40 different packets. Encapsulation is basically taking and wrapping the protocols. So for an instance would be, let's see, for what we did tonight with Eagle, HTTPS protocol, right? You've got UDP protocol, you've got TCP protocol, you've got IP protocol. All of those protocols are wrapped in that just one little session of sending your name into the lab. And the physical layer transmits that frame over the network. And here's the overlap. As you can see, from application to presentation to session to transport to network to data link to physical. And you'll notice on the last four, the data is starting to be segmented. Now, one thing I mentioned earlier, when it's being thrown out onto the network here, okay, when it's flowing onto the network, it's actually going across the network in multiple zeros and ones in the binary format. When it comes back to the other side, it takes that binary digital format and converts it into whatever the presentation needed. In that case, it might be a video, it might be a text file, it might be a PDF, it might be an MP3, right? So it converts it from that digital format to whatever package it needs to be presented in and whatever software is being used. Eagle, what do you guys use to play music? Give me an example of a music app you use, maybe.
Spotify.
What is it? Spotify. Anything else you can think of that you use that package? What about image stuff? You got to do any Photoshop people? Any image manipulating people in here? Like to manipulate graphics? I was a graphic designer for years. A kind of weird bunch of people. So, any software you could think of used to manipulate images? No image manipulation. What is it? There you go, Paint. Yeah, exactly. It's been around for a long time, right? Easy one to use. And so, opens up into Paint, views that image, right? Now, what if I try to open up an image in Word? What would happen, do you think? Could I do it? Or if I did do it, what do you think might I see if I opened it up? What do you think I might see? Just take a guess. Text, yeah, a whole bunch of garbled text. You might see at the top of it, at the very top line, say you imaged it in photo or in Paint, you created it in Paint and saved it. At the very top of that text would be Paint version 6.0 or something, and the name of the file or whatever, and then a whole bunch of garbly stuff after that. So you could open it up in that, but it's not meant to open up in that. And this model basically doesn't show what it's opening it up into, it just says it's packaging it to open it up in an application, okay? Whatever that application be. Frames. The frames basically referring to the different cabooses going across the network, and it basically has network type where the frames flow, and they have to follow a certain standard. And then Ethernet, developed, believe it or not, by Xerox way back when. And when you think of Xerox, what do you think of? When you think of Xerox, what do you think of? Yeah, printers, right? You think of printers. Because, you know, their whole reasoning for Ethernet was to get their printers networked for people to print from, which was pretty ingenious, right? I mean, makes sense, right? You have an office, why not network it to print to a printer? So Xerox spent time and money to do that. And so developed 4 types of Ethernet frames. The most popular, still around today, 802.3 standard, IEEE, 802.3. And another one used by Token Ring we talked about when we did the layout of the different ways that you can create a network. That was developed by IBM, nearly obsolete today, but still around in some banking, military facilities. IEEE 802.5 standard for Token Ring. Ethernet frames and token rings differ because they will not interact with one another, and devices cannot support more than 1 frame per physical NIC. A lot of times Token Ring will have multiple NICs, one for in and one for out, just because it can't work on one NIC in and out. 802 whatever, that's what we're talking about today in present day. Basically, this standard on the IEEE network is basically dealing with connectivity, addressing network media, error checking protocols, encryption. And then 802.3 is the Ethernet, the cabling. And then 802.11 is all the wireless platforms from A all the way to present day N technologies, which most of you probably have an N router at home, I'm guessing. And they're backward compatible, meaning if you have an older device that only works, it's a NIC card that only works on a wireless NIC card that works on a B or a G, it'll work fine on an N. But you have to generally set your router to what's called a mixed mode. And a mixed mode will actually be a little slower, but you'll be able to connect older devices. Like say if you have an old, I don't know, Nintendo Wii or something maybe hanging around, or an old console game or something that connects to Wi-Fi, you might have to do mixed mode. Because true N mode is much faster, but it only works with newer devices. So here's all the standards from 802.1 to 802.22. You probably heard up to maybe up to 802.11, which is the Wi-Fi standards. But notice 802.15, wireless PANs. These are the coexistence of wireless personal area networks with other wireless devices in an unlicensed frequency band. Now, just guess who you think uses this the most. And I'm going to keyword unlicensed frequency bands. Who legally uses this the most? I'll use that, might be a better way to put it. Who legally uses this the most? What type of entity uses this the most? Military, yeah, military uses this the most. All of our Wi-Fi standards that we have today were implemented by the military, some group in the military, multiple groups in the military, over years of testing to get to where we are today. Every single one of them. 3 years ago, I had a student here that was a U.S. Marine Corps IT Wi-Fi specialist that worked in the field for 5 years, and he shared what he could in his presentation about some of the things that they tested, because it was already out there in the public. It was kind of interesting, some of the stuff that they're able to do. And one of the interesting points I think he made that was kind of shocking to me was, maybe not to you, but it was to me, was during wartime today, still, even today, we're still using really, really old, antiquated communication because the Wi-Fi security, even today, with the way it is now, the WPA2, is still not good enough to send top secret information from troop to troop with just Wi-Fi. Now, will it get there one day? I think so. I think it will. He thinks it would. But that's the kind of stuff they work on. And so they're generally, he was telling the class at that time, usually 3 or 4 versions ahead of normal everyday folks that use Today we're using N standard, and WPA2. These are 2 or 3 versions ahead, and it takes anywhere from 4 to 5 years for each version to get passed into law and to standards. So that's kind of cool. But that's the wireless PANs. And then 802.16 broadband wireless MANs. This is atmospheric interface related functions. And this is referring, you might have heard this one, WiMAX. WiMAX is a term you might have heard of. In fact, if you go to Schaumburg Mall, Clear Communications is a store you can stop at. And if you live in that area in Schaumburg, you can get Clear Communications and basically have Wi-Fi access within a 30, 40 mile radius of the WiMAX station in Schaumburg. Chicago has it as well. Why is it not at Rockford yet? All I'll say is from talking to Clear Communication people, politics is a lot of it. It would compete greatly with who you think? Comcast and Xfinity. But I think probably what's going to happen, and again, I could be wrong, I've been wrong before. I think eventually Comcast will buy out Clear Communication. And this salesperson kind of hinted that. When that happens, well, yeah, people can get it, but they're going to pay the Comcast fees, Xfinity fees. Right now, I think the going rate, the last time I checked, which was a year ago, it was $45, was a low package, a month, and that was for, what was it he said? It was it wasn't a lot, but it's like about 10 gigs a day, 8 to 10 gigs a day, which really, if you think about it, that's quite a bit. But, you know, they're pushing the limits. Now, if you live in Kansas City, Missouri, Google has a spot there. My cousin lives there. Google Fiber is in KC. If you live there in certain regions, you get internet totally for free. They've been that way for 3 years now. And again, cutting bleeding edge of fiber. And that's also being right now, a city is supposed to be chosen between us and Chicago somewhere for the next Google Wi-Fi hotspot or WiMAX with fiber. And so that'd be kind of cool. That'd be kind of great. And a lot of people lobbying for that to occur. That'd be kind of great. Now, Xfinity wouldn't like that, but Google's pretty powerful. They got some money, I think. They got some lobbying power, maybe. Next is the 802.17 resilient packet. This is access method, physical layer, manage what's called rings, called a sonnet in this one. And sonnets a lot of times have to do with point-to-point technology with satellite and dishes. Next is 2.0, which is mobile broadband wireless. Packet handling and other specific for multi-vendor. It's called mobile WiMAX. Verizon is an example of this. Probably pushing an envelope, I'm guessing, more than anybody. AT&T is kind of behind them, but Verizon, I think, is cutting edge, bleeding edge, where you can get little boxes now in your home. I think the cheapest is like $80 a month for a pretty good data package, and you can just take it anywhere you want, basically, and you have Wi-Fi and cellular, right? And then 2.2, wireless regional area network. This is basically wireless broadcast to operate in UHF, VHF frequency, formerly used for TV channels. So you remember when we switched to digital, right, over the air, which most of us did. I dropped cable internet or cable TV way back about that time and went to just over-the-air TV, and then I did have to, because of necessity and speed, have Xfinity for internet, but I no longer have Xfinity for cable TV. And so they're going to be using, I always wonder what they're going to be doing with that. The UHF VHF is actually going to be used and is being used in test areas for internet. That's kind of cool. And so it's the same signal and everything, but you're being used to broadcast internet to remote locations, like farming facilities, places like that. It's kind of cool. So now we're going to show you a video. Let me end